So I'm a professor of computer science at UT Austin. I've been there 10 years now. My specialty is computer vision and machine learning, and the two really go strongly together these days. More specifically, my specialty is recognition, so high-level understanding of images and video such that you could recognize the objects, the people, the activities, the events. These are the kind of problems that we work on. Okay, so my work there, I manage and work closely with about 6 to 8 Ph.D. students, postdocs, and then I teach courses. And so what I'll share with you today is a sampling of a part of our research that is focused on understanding video automatically, and specifically trying to summarize video. So to kind of set the stage, there's no surprise that there's such an explosion of visual data that we're suffering from, enjoying, it depends how you look at it. And this is really exciting for a lot of reasons, and for a computer vision researcher, it means it's all the more important to be able to have automated methods that can make sense of this data. Right? And there's many, many statistics we could look at to kind of characterize the explosion. One I like is that today, if you wanted to watch all the video just uploaded to YouTube today, it would take you 82 years. Okay, and that's per day. So we know that there's plenty more pixels coming at us than human eyeballs are going to spend time making sense out of. And that's where our work could come in, right? Having computers that make sense of this visual data. And furthermore, this visual data comes from many walks of life, right? Consumer data about personal photo collections and videos that we want to share easily, but also scientific imagery that's very important to furthering the science and doing the analysis at scale, in defense, in intelligence, and in art. So in any of these domains, you have very important information, often locked away, except for human engagement inside a disk. Okay? All right, so this is kind of the explosion of visual data, the need for scale, the need for algorithms to make sense of it. And I'm going to talk specifically, as I said, about summarizing video. And I'm going to get even a bit more specific than that and talk about our work looking at first-person or so-called egocentric video. And all this means is this is camera data that's coming from a wearable camera. And back in the day, the early years, it took a lot of commitment to wear a camera. As you can see from this gentleman here, Steve Mann, who's now at the University of Toronto. But things have changed. So now if you want to wear a camera, it's not such a commitment. And this is fine. It means it's practical. It also means there's much more push now for the applications in augmented reality to bring computer vision onto these portable cameras and computers. And when I think of first-person vision or wearable camera data, it's not limited to human-worn cameras. It also includes cameras on vehicles, so autonomous vehicles, self-driving cars, as well as cameras on mobile robots. Okay, all of these offer the chance to do visual analysis from the first-person perspective. And in fact, in the research community, in applications, in industry, you could think of it as a new era for first-person vision. And again, I think this has to do in pretty good part from the miniaturization of these devices and what you can do. So one that may be most familiar, augmented reality. So we'd like the ability to mix kind of the real world with the virtual world. And if you're going to do that optimally, you'd like to know what's in front of the user and what they can see so that you can blend these things together. But there's other applications as well that are quite interesting. So plenty of us like to quantify a lot of things about our health and behavior. For example, you can imagine a wearable device that's watching what you eat. This is not what I want, but that could, categorize and understand the health of the food that you're consuming. And people look at this. Law enforcement, certainly we've seen a lot recently about the potential for greater transparency between law enforcement officers and the public if these officers are wearing cameras. And increasingly they're doing so. Body cams usually worn on the chest. Okay? So opportunities there for this kind of technology. Others in science. So this is really fascinating. Psychologists will look at the observations they can get from first-person visual inputs on infants who wear cameras. Because if you think about it, if you want to really understand at scale from a lot of data how word acquisition happens, how motor skills develop, and so on, there's great resource in knowing what the infant experienced from the first-person point of view. Robotics I already mentioned. And then down here, life logging. So early adopters of wearable cameras cared a lot about life logging and this idea of being able to never turn the camera off and always have these observations coming in. And that really motivates what I'll tell you today about summarization. Okay, so just how different is it to have a wearable camera video from an everyday third-person camera video? Well, you're looking on the left, a traditional third-person video. That just means it's a static camera pointed at a scene. And here's another video, also of a mall, but this one's from the first-person perspective. This is from a head-mounted camera. And you can see right away that qualitatively there's very important differences here. On the one hand, I have a nice, rather stable view in the third-person perspective, and I kind of see a static environment. On the other hand, on the right view, it's still a mall, but now I'm getting more challenging video to deal with, but at the same time, I'm getting cues about importance and interactions, what someone touches, where they look, and that's coming from the raw video itself. Okay, so when you develop computer vision algorithms, we actually have to be very conscious of this difference. And so we say, in the third-person point of view, again, here viewing the same kind of activity, third versus first, you're really more experiencing the activity from the first-person point of view. And so as a vision researcher, we are conscious of this link. Really, first-person data is about the story unfolding in front of a person wearing this camera. And when we analyze this video, we need to account for this inherent link. Okay. So let's talk about summarization. The goal in video summarization is to take a long video as input and produce a short video or a storyboard as output. So a long video comes in and a short video should come out. And this could be, say, a daily life activity video. Again, the camera's always on, just what are we capturing? And the bottom would be a kind of summary that we might like to come out. And this summary would be automatically chosen content by the algorithm that says what has happened across the daily events. So that's the goal, long to short, and you can hopefully start to see why this would be quite valuable when you think about the reams of video that any of us have, that scientists have, and that we want to map down into the most important parts. I got motivated to explore this question by learning about how wearable cameras worn by someone suffering from memory loss could actually help them regain some recall. So small studies that were done by psychologists, just looking at someone who wore a camera that would fire maybe once a minute, and then just re-seeing those photos at the end of the day could help relive a visual experience and have a greater memory of it. That's pretty intriguing, and what if we can have computer vision systems that are smart about which of those photos even need to be taken? Okay. So that's a good application area. I think law enforcement is another one where these kind of summaries can have great impact. So what makes it challenging? Well, again, you see this kind of free-form, egocentric video and how difficult it might be for a computer, let alone us to watch it, but for a computer to watch this and really make sense out of it. There's a lot of technical challenges. Some of them include that event boundaries are subtle. So this is just ongoing activity. There's no nice clean break. Like in the film world, you have a shot break. It's obvious when the camera has moved, and we're very good at detecting that. It's not the case here. This video is just ongoing, very fluid. There's also subtlety in the figuring ground. There's also long streams of data. So anything we do on these videos, if it is an always-on camera, they have to be quite scalable. So when people started looking at video summarization, and there's plenty of work over the years doing summarization itself, it's largely been for third-person data, the kind of static camera like we looked at a few minutes ago. And furthermore, you can think of traditional methods as looking at this as a sampling problem to kind of maximize some criteria that would keep things diverse. Just sample intermittently. And this really isn't enough when you look at the kind of challenges in the first-person video. So one idea we've been exploring is to try and discover a story-driven summary. What makes a good story? Well, a good story revolves around some key players, key characters, and the plot, right? So take that as very loose inspiration for what are the things we need to capture if we're going to extract a story out of a long video. Okay, and so when we do this, that means our computer vision system is going to need to be able to decide what objects it sees, which objects are important, and then how are they linked over time to create a story that has a notion of progress. Okay, because if I just sample things at gaps along the video, and now I show them to you, that doesn't mean it'll reveal to you kind of cause and effect and how one thing led to the other. And that's more what we want. So to give you a toy example, suppose there was a video about someone making tea. Well, then the system ought to have picked up ideally even in an unsupervised way, about an object like the teapot leading to getting water, leading to making the tea, leading to you sit on the chair. Okay? Just as a toy example. So that's the kind of flow we're looking for. And so what we've been doing is developing the computational means to go from raw video to objects that we can detect and extract, to ratings of how important those objects are to the story, to furthermore, most challenging, what's the influence between those objects that tells you how a story unfolds. Okay, and these are very general terms and terms that, okay, when we look at this problem, we're having a series of subshots. We need to decide which of these we keep and which of them we discard. Okay, the ones we keep will be the summary that someone could watch to understand the video. So what this is saying is find the best subset of these shots that will have a lot of influence maintained, a lot of importance maintained, and a lot of diversity so that there's not redundancy in the summary. And our job then is to develop ways you can actually compute these things so that the system knows how to optimize all of these criteria. So to give you a sense of what this looks like, first, when we have an incoming video, the first thing we need to do is to chop it up into subshots. And again, kind of the traditional approaches are often inadequate for first-person data. We've done things like, we can learn to recognize different, what we call ego activities, so whether someone's static or they're moving or their head's moving about. Then you can think of dividing over time the video into these chunks of mini events. Okay, so this gives you subshots to start reasoning about. Now you need to know which of those should I keep, which one should I drop. And our decisions about all of that are going to be based on how well can we find the objects in the video, and most importantly, which ones matter and which ones don't. So here are a bunch of sample results from some of our very latest work where we have a deep learning approach we've developed that can take a raw video like the one on the left and segment the foreground object it has discovered. In the video, you see the output on the right where the object it's discovered is outlined, shaded in red. Okay, in the middle, this is some intermediate computation about the motion that's detected within the frame of the video that's fed into the learning algorithm that's able to produce the one you see on the right. So this is actually fully automatic. There's no human intervention to figure out the objects that are important on the right. And these are state-of-the-art results to find objects at the pixel level within video. Okay. So it gives you a hint now of how the system's starting to parse, find an object that it may never have seen before, but realize that it's important and precisely where it is in the video. Okay, so we can find these objects, and now we look to egocentric, meaning wearable camera data, and we want to decide, or in fact learn, when is an object important? So if you think about it for a minute, if you're talking about first-person wearable cameras, there are, as I alluded to, special signals about importance and saliency and attention that come for free within this first-person view. So does anything come to mind? What kind of cues would indicate from a first-person video whether an object, such as any of the ones I was highlighting in the previous, is important to, say, daily life activity? There's signs that we get. Yeah, so if the object's centered in the view. Right, especially if we have a head-mounted camera, we have nearly a proxy for the gaze. And so, we can turn our eyes without turning our head, but the coarse motion will keep the important things we're attending to in the center. So there you go. You have a spatial cue about importance that we can capitalize on. And there's others. We can look at things like, did a hand ever touch it? So when you wear a camera, much of your body is not visible, but the hands would come out to touch and interact with objects. So you can extract features about this. You can extract, as we said, about the gaze, how often an object is happening. We have high-level metrics of saliency that we can use to gauge importance of these objects. And people are so important to everyday life activities, so knowledge about how far these objects are from people. Okay, so imagine extracting these things, just computing them from the video frames, recording them, and then learning, say, a regression model that can go from these features to how important any given region in the video is. So now the computer can start to learn. You show me a new object, I, being the computer, can estimate how important it is for this story. And what's important is we can do this in a category-independent way. Okay, so we're not going to learn that dogs are always important, but we'll learn when, given the situation of the story in this video, the dog looks important. So let me show you an example result from one of our data sets with a head-mounted camera. So what you're looking at on the left is a video that I'm excerpting from about 3 hours of content. Okay, and again, daily life activity, which is motivated, again, from this thought that we might be able to help someone with memory impairment by being able to compress their day, their everyday life, into short visual summaries. Okay, so here's the original video on the left. Now what I'll show you on the right is a summary produced by our system that's just 12 frames long. And you should look at these 12 frames in sequence and decide, can you tell the story of what was happening in this daily life activity? Here we go. Okay, so did we see it? There's a bit of a story there, right? Driving to the store, getting some ingredients, getting a recipe, cooking, preparing, enjoying some food, cleaning up, right? And you saw those very carefully selected by the algorithm, these very carefully selected frames that reveal that story in a very short amount of time. And that's exactly what we want to achieve, right? This is a qualitative example of what we can get. And now, of course, yes, question?
How long does that take to translate 3 hours to both frames?
How much computation time does it take? In this implementation, quite a long time. And the bottleneck for us is the region computation, the segmentation we were using at the time. So this isn't close to real time. I think that a lot of the future computation could be close to real time. But one thing to keep in mind is when we compute these summaries, we're doing a global view of the video that has the ability to look forward and back in time to make its decisions about what it should keep. Yeah, so I don't have a number for you. Because it'd be embarrassing, I suppose, right? This research code and proof of concept for what we're doing. But we would spend, for the kind of region extraction we were doing at the time, we would spend, we could spend 30 seconds easily on a frame, right? So think about that, and then think of 3 hours of video. Yeah. So when we do this, then of course, this is just a glimpse, a very qualitative glimpse of the kind of things we get. I'll show you another one. We compare what we're getting to other kind of techniques you can do, like any kind of a simpler sampling, existing algorithms in the literature. Right now, just to give you a taste of what we do, I'm showing you some of our results. Here's one where we're creating a video skim. So what our system is doing is finding little excerpts or little glimpses into the video that it wants to keep, and it's concatenated the ones it wants to keep that you're watching on the left. Another daily life activity, this is someone at an ice cream shop, got some ice cream, paid for it, now they're watching TV, and then they'll go on and go outside for a walk afterwards. Now, had you just uniformly sampled among the subshots that are there and kept those, you'd get the one that I'm showing on the right. Okay, and now that you know the story of this daily activity, you piece some of it, but you can see that it's missing kind of some of the highlights, the important actors, and then how they string together. So these are qualitative examples from some of our head-mounted data. Another thing we've tried is to play a little bit with the visualization. So we're really on the vision side. We work on the learning and how do you optimize the things that even need to be kept. But there's a lot of opportunity for visualization in the graphics side of how do you display what you found as the compact summary. So here's one where we took the spatial coordinates of the selected keyframes and plot for, in both time and space, the mini story that was found. So now you can kind of see the story of this person's day, where they were in Austin at each main event that the algorithm decided was something to highlight. And I think this just suggests a little bit of possible applications for sharing and social kind of applications of daily life activity or others. Some of the challenges that come with this problem space are evaluation. And that might already be bothering you right now, just sitting here watching me show you results where I say, oh, do these look good? Well, we need to pin down just how well are we doing anytime we do video summarization. The bottom line is it's a perceptual task, and the success of a summary has a lot to do with the task domain and what a summary needs to convey. And so there can be subjectivity to that. So we put a great deal of effort into user testing, kind of show people 2 summaries of the same event that they've read about in text, for example, and see which one captured it better. This blind taste test is kind of doing something like this, where we'll see how often they prefer our summary to that of another algorithm's. And so we do a lot of this kind of testing to try to get numbers to attach to how successful or not successful the method is performing. All right, so this was kind of idea 1 that I wanted to share. And I'm going to share the second one briefly and then the third one here. So we're here, I just talked a little bit about how a story can be told through important objects that a system can automatically detect in video. The next thing I want to describe builds on egocentric data again, and now thinking instead of creating the story, let's just flag those moments in time in the moment when a person is engaged with the environment. So again, wearable camera, and can we decide when they're engaged with the scene? So imagine scenarios like this. Maybe you have a consumer looking at products in a store. If that consumer is wearing a camera, the camera and the computer on board would be able to detect when they've slowed down to investigate something more closely like a product. Similar kind of things in museums, anytime we're browsing an environment and our attention kind of ebbs and flows. Or in outdoor environments, say these people, attention may be gathered to something unusual that they see. Okay, so we make some formal definitions of what it means to have heightened engagement. And then our goal is to take these video streams and be able to flag those time intervals when the attention has been heightened. Okay? And I'm looking at this as a purely visual way. Of course, you can think of other modalities that signal our attention, the skin conductance, for example, heart rate, and people look at these kind of channels as well. In this case, we're looking at it purely from the visual, the video flowing through. What does what I see tell the system about how engaged I am? So we've gone about this in a machine learning-based approach where we will learn from supervised data when are those moments in time when the person wearing the camera was engaged. And so part of this effort was some data collection, 14 hours of labeled egocentric video, and I mean labeled to the frame level for whether it's in heightened engagement or not. The kind of data we get from these browsing environments like shops and museums and markets looks like this. All of these are excerpts where 10 human judges would say that the person's engagement was heightened. And what's hard is these things look all different, right? So you're not going to build an appearance-based model that says, okay, this looks like heightened engagement. That's a hint at our solution. Furthermore, being engaged with the environment is not the same as being stationary, which might not be immediately what we expect. When you think about shopping or stopping to peruse something, you imagine being stationary. But with these head-mounted cameras, there's quite a bit of activity even as you're pausing to investigate something. Okay? And then there's other technical challenges more on the vision side about why this will be hard to do. So our approach in one slide is to learn the motion patterns that are observed. So this can be independent of the appearance itself. The motions patterns that are seen will suggest when engagement is occurring or not. Okay, and I'll show you some sample video. This is our result. And here, when you see it red and blue, it means things worked well because our prediction agrees with the ground truth, meaning an interval where engagement was heightened. If it's blue and it's not red, that means we've missed it. Okay, so here's some data from a museum. And now the person is engaged with the environment investigating this individual site, and we're predicting it as such. Okay, so these are all good examples in this stream. Okay, and you notice the temporal interval also varies in length to when the engagement is happening, and the system does a fairly good job in these cases of identifying the right interval. There's one in the shopping environment. Going around, and you see there's plenty of motion just looking about, but when engagement happens, for example, here looking at the sign up there, the system is able to detect this. Okay. And I think that sign is probably a good example of a case where the visual input is really crucial to understand engagement. This isn't something I would expect that's going to make the heart rate start pounding, right, to see the sign of where I'm going, but it's investigating and it's visual, and you really need the video to be able to detect that. So these are all good cases where we're able to decide, okay, this is when the user wearing the camera is paying more attention. These are cases that we did not do well in this next video. Kind of places where this learning-based approach, looking at the video motion to decide when engagement occurs, does not do well, are things like when the interesting thing is already in the line of travel of the person wearing the camera, then it becomes indistinguishable as far as the motion patterns are observed. Or if the person's doing quite a bit of head motion, but there's nothing that they're attending to, we may be confused. And certainly, in this case, we have more direct ability to quantify. These are precision recall curves, higher is better. We look at all smattering of existing video saliency methods to try and see if they're adequate, as well as off-the-shelf deep learning convolutional network approaches to do this, and we can claim some good results and consistent results on being able to detect these activities. So now I'll move to the third and last part of this talk, where I want to share, again, on the theme of video summarization, some of our very recent work. But now I'm going to move from a strictly egocentric camera to 360 cameras. Okay? So if we thought we had a lot of pixels before, now look at what we have. Right? So 360-degree cameras capture the visual world from all directions surrounding the optical center of the camera. All right, so widest field of view that we could possibly have, a spherical panoramic view surrounding the camera's source. Okay, the market is growing quite a bit for these cameras, so It's expected to grow by more than 100% per year, just the sale of these 360-degree cameras for the next few years. And at the same time, content creators and content hosters like YouTube, Facebook are ramping up efforts for how people can view this 360-degree data. Okay. Has anyone in the room watched a 360-degree video? Just a couple hands, okay. So how can you watch a 360-degree video? Well, different ways. You can put on a headset, right? VR headset, and you can watch the video, and your head motion then will say where you're pointing your eye cameras within the full view. Or you can do things like on YouTube where you click around a virtual camera. So it's showing a subset of the 360 data, and you move the camera to where you want to turn it with a mouse, right? Or you can do something like unwrap the panorama. So right, it's just a sphere of the viewing sphere. You can unwrap that with a lot of distortion and put it down on one plane so a person can watch the whole thing at once, but incurring all of this distortion. So let's look at this common kind of online way that people would view 360 data. Here's a video, and I'm using it to illustrate the point that this is very much in need of some form of summarization. In this case, it's not necessarily so much temporal summarization, but spatial summarization. Okay, because you've got this massive 360 view, and as a viewer, a human viewer looking at this, I don't know where the interesting stuff is. And in fact, as I'm clicking around, here the interesting stuff was behind me. Had I stayed forward, I would never know about the elephants on the other side of the camera. So, quite close, in fact. Right? So this is pretty intriguing. If you think of it from the point of view of video summarization, now you're talking about not necessarily not just which frames to keep, but which virtual viewpoints do I keep. And so we've set out within the last year or less, we've set out this new problem of we call it pano to vid, so panoramic video to normal 2D watchable video. So we're going to take the 360 video as input, and our goal will be to control a virtual camera, as represented by this viewing cone here, over time, that will then produce a video that's easily watchable. Okay, and just to step back for a second, I think what's really wonderful about 360 video is also very difficult about it, and it parallels kind of the wonderful and difficult parts of egocentric wearable data. You have an always-on camera, but the problem is it's always on, so you need to be able to sift through to find what's important. Here you have an everywhere camera, but the problem is it's everywhere, and you need to sift through and find what's important. So these kind of things, they just parallel. We're talking about temporal summaries earlier, now I'm talking about a spatial summary, and you can, of course, put the two together. So the approach we're taking, let me try to describe a little bit how this possibly works. How do you have a computer that knows where to turn this virtual camera? And then I'll end with a few video examples of what we're getting. Okay. So we want to be able to handle unrestricted real 360-degree video. This is in contrast to prior work, usually in computer graphics, that attempts automatic cinematography, usually trying to translate the rules that human videographers use to make good film into algorithms, which means kind of trying to translate some heuristics. Here we're going to try and take real 360 video and learn these tendencies from data so that the system itself kind of watches video and understands how to create real normal field of view video. Okay, and the kind of things it's going to learn are what is capture-worthy and also proper composition. And the composition is a big part, as we'll see in a minute. So our approach looks like this. We treat it as again, as subset selection problem. So I've got all these possible glimpses, all these ways that the virtual camera could possibly look, and they can do that at every time point over the series of the long video, right? And so a little spatial temporal glimpse would be a little excerpt on this viewing sphere with some short length, say 5 seconds long. So any of these glimpses are there for the taking, and I want to know which one should I keep and how should I string them together. And so what we do is extract these glimpses densely across the viewing sphere, and then we learn in a very data-driven way from unlabeled video, just video that we're grabbing off of YouTube. We have some 300 plus hours of it that represents kind of the manifold of what human-captured video looks like. This is normal field of view video that you or I might take. Then the system can measure, well, just how close is any candidate glimpse that we're considering to this manifold or this big pile of unlabeled video we've seen before. I'm saying unlabeled, it's kind of jargon for the vision world because it means no human has gone in and done anything to this video for our benefit. It's just raw video that the system can look at and learn from, right? And now it learns this model of what's capture-worthy and how to compose a good frame. Okay, so we have ways then we can measure this. And these are the kind of things the system would discover seem to be highly capture-worthy. These are frames from glimpses that it selected. These are those, for example, that it would say is very low on the capture-worthy meter. And it's kind of interesting here, as I mentioned, composition. So these both have people as prominent within the video. But the system rates this as not so good because of the composition of the frame, right? This is a good shot of a person. This is a poor one. And we didn't have to hand code any of this. It's just learned from these 300 plus hours of the video that it saw. Okay, so then the last part of method then is you have the ability to rate how capture-worthy any given glimpse looks. And now the system will find a path through these glimpses over time. And we have fairly efficient ways to optimize that path and furthermore to suggest different paths. Because as you might be sitting there thinking, there's not just one right answer in terms of the virtual views that I need to select from this video. So learning-based approach, learn what's capture-worthy, take the new video, string together a set of capture-worthy glimpses. We've been testing this on data from YouTube, both the 360 video we get from YouTube as well as the so-called human cam, meaning the normal field of view video, that unlabeled pile of video. We're doing it in domains like you see here so far, hiking, mountain climbing, parade, soccer. A lot of video you find for 360 data, often kind of extreme sports, much like the wearable data. You know, people use these to capture interesting moments in extreme sports, but also outdoor activity or special events like a parade. We compare it to a series of things. We're the first really to attempt this precise problem, but we compare it to things like computing traditional video saliency, which is more low level in terms of its interest points, or things like, well, what if I just tend to look at the eye level prior of where a person would hold the camera? Okay. And here we have some pretty interesting ways to quantify how we're doing. One that we've come up with is to say, okay, well, you're as good as you are able to make the videos our system produces be indistinguishable from those that are real human-captured videos. Does that make sense? So if you looked at that pile of 300 hours of video, can you build a good discriminative classifier that can tell that apart from the kind of video you're producing? If you can, then you've failed because they should look like they're one and the same as far as the distribution of the data. Okay, so that's these kind of measures you're seeing here. We're able to compare our approach to these different baselines to see how well they succeed at looking very much like a human-taken video. We've also done some direct things for evaluation where we ask humans to edit the video. So I mentioned at the beginning, you can unwrap a panorama in various different projections and then show the whole thing at once. Here it's shown kind of wrapping around with a little bit of redundancy, so you get the sense of how it connects. And this is what a human navigating the video with a mouse would select their output video. Makes sense? So someone watched the top video, they held their mouse over it, as you see in the cyan box, and whatever they selected is what the video is on the output on the bottom. So another way to see how well we're doing is to say, okay, the videos our system pulls out of that top video match at all with the one the human editors would choose. The more they match, then the better we're doing. So we have metrics of this kind to look at that agreement, and things are looking very good. So maybe the most enjoyable part of what we're getting, let me just show you a few examples. So again, the input video is the top one. And output here is what our system's creating. Okay, as it's one of its top hypothesis of what a good watchable video would look like given this 360 content. And what's kind of interesting about this one, we notice some, non-hard-coded, purely learned behavior where it's starting to track some of the objects like the balloons that are released from these ships, and then it moved from one ship to the other in its viewpoint. This is another example of a hiking video. Our output is on the bottom left. One of the baselines is shown on the bottom right. And here you see what we're able to get from the composition that's learned from the unlabeled data because it's framing the subjects a bit more naturally than the one, say, that just uses an eye level prior. And the third and final example, I think this is one of my favorites. This is a video at an aquarium. The 360 is at the top. Here we've augmented our algorithm with the ability to zoom in and out. And on the bottom left, you see the result where it decided to zoom in onto this diver who's then starting to move, and then, again, purely from its learned behavior, it starts to track the diver a little bit as it moves over and scares this child. Okay. And the one on the right is also our method, but before we would have the capability to do zooming. Okay, and so that was when we had a static focal length for the virtual camera, and now we have the ability to dynamically change it, and we get that much more control of the automated camera. Okay, so these examples give us a sense of how we can go from too much data in time, too much data in space, and come up with some things that are human intelligible, but yet, despite the fact they're algorithm selected. The kind of things we're working on now that we need to do in the future are some that you see here. One that's intriguing to me is to think about how to evaluate the success of your summarization in terms of how well it allows you to do a search task, right? So, and the search task could be any question I want answered about a long video. Well, the naive way to find the answer is to watch the whole video. The smarter and faster way ought to be using a good summary. So if you have a successful summary, then it should be able to allow someone to navigate a video. Maybe this someone is a consumer, maybe it's an intelligence agent, whatever it is, should be able to navigate this video faster because the summary was smart about what you need to see first, right? So this is one idea. Learning to summarize from examples. We've done quite a bit of work most recently on how to learn from examples of summaries. So in the events that we have, even human-created summaries, we can learn kind of the meta rules that allow you to go from long video to short video in the way that human examples have shown. So we have some pure learning ideas for how to do that. Streaming computation, so related to a question earlier, there's trade-offs between whether you process this video in batch or whether you do it in a streaming way. Okay, it just depends on the setting which you need, but there's some fun challenges for us to think about how do I make a good story when I can only look forward in time, right? So I can never come back and change my mind about what I decided to keep or leave earlier in time. Visualization and display, how do we make these effective in a visual sense? And then multiple modalities. So this is a realm of computer vision where we can't limit ourselves to being computer vision researchers because multimodal information is key. Audio is a big one. Haven't really capitalized on here yet, but think of the possibilities for audio revealing the ambient sounds of the room, which reveals the scene, which reveals when things have changed. Think about the 360 video if you have multiple microphones with this camera and the activity is happening behind you or in front of you, you can hear that as well. So those are one important channels. Depth as well. Depth sensing from these cameras could also be valuable. All right. So I want to conclude here. I guess the smallest message of this whole talk is that summarization algorithms are very much needed in order to cope with the deluge of video data, and particularly egocentric and 360 camera data. The new ideas that I told, 3 things. We talked a little bit about story-like summaries, detecting the time periods when engagement is heightened. And then I talked about this new work on deciding where to look when you're sitting virtually within a 360-degree video. These are all the students I was working with to do the work that I shared today. And I thank you so much for your attention. We'd be glad to have any questions, comments, if there are any.
There was a movie done years ago called The Final Cut. Are you familiar with it?
No, I'm not.
It was a movie with Robin Williams, who played an editor in the future, whereby people had implanted chips in their brains that recorded their entire lives. He then would go in and edit their lives.
Okay.
You were talking about the algorithm making decisions that might be different from another subjective point of view. Mm. So I was wondering if there will be a time when we will have that capacity, since it's just a matter of storage space. We will be able to record somebody's entire life from their point of view.
Mm-hmm. Yeah, it seems we're closer to that goal than we are to the goal of shortening it intelligently, right?
It's a good movie, by the way.
I think I'll check it out. Thanks.
Thank you so much. Very, very interesting. I just had a very technical, because maybe I don't really understand all this, but from what I understand, the way that your algorithms zone in on what to pay attention to is I think you mentioned the bigger object in your primary view, and then sequentially just find one object here, and then it somehow based on that chooses how to summarize it. So I just wonder. I'm trying to sort of compare it to deep learning techniques for natural language processing, which I understand now they're working with the lexicon of how the algorithm understand synonyms, and like that this word is closer to that word, and it can kind of create an understanding and uses that as training data for future iterations to learn more and more and more. So I just wonder, I guess it's very difficult for optical data, because then how does it already know what that particular object is? It signal or noise? And how does it put all these scenarios together? So you have the coffee cup, and you had the brew or something, and then you had the television, so it understands that this tends to go together. But then how does it understand various different scenarios?
Yeah. Well, and there's so many possibilities. I guess a couple things to note. So it's interesting, there are some nice parallels between what's going on in natural language processing with or without deep learning and in computer vision, and including things what you're alluding to, I think, like semantic embeddings, where we understand in an embedding space, some representation, what words are related or synonymous and co-occur and so on. You can do these things, and people do on the visual side as well, learning, which patches or frames of video or image should be mapped close or far based on their semantics. And so, for example, if just as you might teach an NLP system that these are words that mean the same thing, and maybe you discover it from co-occurrence in large corpora, you can do that kind of thing with blobs of things that appear in video, and what things, that these things are semantically close, and now we learn the visual relationship between them. So there is that nice parallel for sure, and people exploit it quite a bit. As far as how do you pick the things over time, I really didn't go into any detail about this, but in the first part of the work, the kind of thing we were leveraging is that, yes, we can say kind of these unary terms about, okay, in these subshots, here are important looking things, you could score them all, but you're not done, because like you said, you want to string them together, and which goes with which. And so the angle we were trying to pursue here, and it's far from finished, is to say, it's not enough for us to know which things typically occur together, because that doesn't make a good story. I can't just say these are a lot of similar things. What I really want to capture is that this thing leads to this thing. Okay, so this notion of progress, and we also refer to it as influence, right? And so if there's a forward motion between an object leading to another object that tells a story, that's what I want. We have a computational way to get to this. Imagine building a big graph over these objects and then doing random walks that tell you how connected different objects tend to be, just based on what you've seen in past video. It gives you a hint of like what we're able to compute to then maximize the influence of the exerted subshots that we keep. Yeah.
Thank you.
Yeah.
About doing narration over the video, just more machine learning narration.
Narration, as in
Just
narrating
as
the
in-
raw video, or
As if it's a show, right? So even where that diver scares a child, right? So if you could use trained data to, from subjects that were giving it some kind of narration, could you then predict a narration out of it?
Okay. So during training, the long video has some narration, and what you'd like as output is possibly a shorter video, or at least a video that, for the new content, similarly provides narration. Yeah, it's a great thought. Not something we're doing, but there's scope for it, I think, in the research going on between, again, NLP and vision, and you need a little bit of speech in there too. Yeah, it's a great thought. Yeah, when we try to do supervised summarization, again, we focused on the machine learning methods, which I didn't present here, to do supervised subset selection, basically. There, when you start to think, well, what's the supervisory data? It's not, you might think, oh, movie trailers sounds fun. And it does sound fun, but movie trailers really aren't summaries. They're more art of their own, right? To make a good trailer, it's not really recounting the story. It's just giving you something a taste of it. So other sources are just if people have done it for academic purposes, but maybe narration, what I'm getting to is maybe narration is a good one to attempt for that, right? For the supervision that already exists. And there are sources of data like this, like people look at can't remember the name for this, but the acronym, but basically narrating video for the blind. Right, so that is really nice narration because it's not supplementary, it's really telling the story explicitly about what the visual is. So my colleague Ray Mooney at UT Austin looks at some of this data for bringing together the text and the visual.
Just for the record and for your information, because it was a good question, there was actually a computer that was fed in a movie, and using AI software, it created a trailer. So it did take a narrative, and it did isolate based on a variety of information, a trailer, and it came out really well because it's a specialized area, and people who cut trailers looked at it and they said they couldn't have done any better.
I was curious. One of the other sources, it looks like most of your sources are, YouTube and public video sites. But to do, especially the kind of stuff we've been talking here about the last couple of minutes, it seems to me that a really useful source might be something that would show you what human editors do. Mm-hmm. So there's a lot of really interesting information locked up in, Avid and Premiere and whatnot systems, throughout the world. Have you considered using those, or do you use those in any of your research?
Yeah, it's a great thought, and haven't used them. I think the availability and how to get your hands on such data is one of the first hurdles. Yeah, but it's a great idea, and we do think about just at the technical side related things like even learning from how a person controls a camera more explicitly, right? Or people look at things like doing things like learning from gameplay, like someone playing a game with the visual and how they decided to direct their own gameplay. I mean, it's got a similar flavor, right? Learning from how an editor chose to do their work. So yeah, fascinating stuff. I think their kind of solutions, it can be deep learning, it can be deep learning instantiations of reinforcement learning, to bring this to bear. Yeah. So. Yeah.
Can you give an example of defense and security on how first person versus external? I mean, are you trying to retrain people walking on the ground?
Yeah, so an example where these things would be relevant, you can think of, for example, a soldier as a sensor. So someone who's out in the field and, you can think of wanting recaps or executive summaries for what they've been experiencing or doing, maybe solo, maybe multi-person. Imagine multiple people wearing these cameras and having some collaborative goal. So I think of scenarios like that. If you step away even from wearable and just think about videos that need to be summarized, plenty of aerial video or otherwise that right now analysts need to spend a lot of attention and thought to find patterns of interest or even items of interest. There's a great need for automated means, of course, to do this. And summary is part of it. I mean, recognition is part of it, and recognition in some ways is a lot more mature part of it. Because if you tell me, here's a bank of things you need to find. You need to find trucks, you need to find XYZ. We're much better at training those up and releasing them. But the summary problem is a little looser and softer, and it's more about highlights and what's relevant for the watcher eventually to then maybe dig deeper in a manual way. Yeah.
It sounded like the processing time for training this was far from real time. But once you get into a specific domain, and once you've had some experience with summarizing things in that domain, does it get closer to real time then?
So that would not be the factor in our case. So the training time itself can be very long, especially if you're doing anything with the deep learning component. We can spend weeks going out and train. That doesn't concern us because training is the offline part. Once it's done, you have your box that does what it needs to do, and usually test time is much faster, right, to go through. So I mean, it's interesting what you bring up. Like, could the system, I guess, start to find the task easier because it's done it in a certain domain, and so the computation would get less. The way we're going about it, that wouldn't happen. But it's interesting to think, could you make it such? The main bottlenecks for the computation right now, even the 360 items, are we're spending a lot of time doing the convolutions, just getting the features, because you're getting a lot of frames, a lot of pixels, working through these just basic filter extractions. You have a deep network that's doing the feature extraction. And secondly, in the 360 case, the rendering. So if you think about all these virtual views, we first want to extract the virtual view, render it as normal field of view, and then do computation on it. And that's a bottleneck that we have ideas to make better. Yeah.
What's the underlying infrastructure that you need? How many cores are you running?
Oh, yeah. So it varies. I mean, the computational resources we have available in-house are things like, at this point, 60 nodes in the GPU servers, which we use heavily for the deep learning parts, and thousands of nodes in terms of CPUs that we use in the department. We also are heavy users of TAC, Texas Advanced Computing Center, which has also some good GPU resources there. So thousands of machines typically go into in some way or another, have gone into helping us get results we get for every paper we write. Yeah. Yes?
Is there any specific software you are using, or are you writing one of your own?
Yeah, so when we are programming these things, we often, it varies. We often start in MATLAB. I mean, there's a lot of MATLAB used to do the research, or just quickly prototype ideas. We use some common packages for deep learning when we're doing anything related to that, like Caffe and Torch, maybe a couple others. So maybe that gives you a sense. Yeah, if we need things to have performance, we'll write code in C++. But yeah, I guess in our world, working on the research side, it's all uncertain, and there's no we're going to go from A to Z. It's like we have Z, and we're going to find some path, and so the code and the runtime, as you're gathering from my answers, is very much secondary, and it's really about the algorithms and how do we possibly solve the problem. Yeah.
Quick question, hopefully. Do you, I don't know the right terminology, but would you take multiple videos and layer them to get a summary? For instance, the guy walking through the mall, and you might have 10 people do it to see, the people in the mall would want to know what did people look at and what was of interest to them. Do you layer multiple ones on?
As in, at the display time, let's show multiple summaries, or furthermore, let's co-summarize the things that we
take
saw?
multiple ones and put them into a single summary.
Yeah, absolutely. And it's interesting, I think, from an application standpoint and also an algorithm one, because there is this challenge that we've been making some progress on we call co-summarization. So if you do have video you know is related, and the mall is a great example, right? You might even have similar physical paths. Then how does that redundancy of the data help you more successfully identify the important parts or the anomalies, right? And that's probably, you might care about that too in such a scenario.
Where do you want to put your advertising?
Yep. Yeah, I think the attention and these browsing scenarios, I mean, for me as a novice as that goes, it has good retail possibilities for understanding what people are doing in a physical store with this wearable camera.
You mentioned the difference between the first person and third person perspective in terms of analysis, which is easier?
It's a trade-off, because you can say first person looks harder, feels harder because of the amount of motion and fluidity in the data, and the fact that if it is a camera that's always on, it's very long and ongoing. On the flip side, you can say yes, but you also get aids, such as the ones I mentioned of gaze information and attention and so on, that are signaling things you're never going to get from a static, independent camera. So yeah, it's hard to say exactly. I think in terms of the low-level stuff and what people are used to doing with video, third person is easier. Because it's static, you can get away with some simpler things that have a lot of value, like background subtraction, finding the moving things, or characterizing behavior by very simple cues like optical flow. You can't really do that on the first person side.
Well, you weren't here this morning to see my first video attempt, which was to put together a number of clips from AR and VR. So I poured over hours and hours and hours of online video personally, and selected the ones I thought these guys would like to see. And some of them were like, say, 10 minutes long. And my job was to go through the 10 minutes and try to extract 3 minutes, which wouldn't be just one clip. It would be from particular points, your sub-videos, if you will, and put those together into something that continuously told a story in 2 minutes instead of 10 minutes. I have so much sympathy for your computer. That is a hard, time-consuming job. And every time I see a movie from now on, I'll be looking for the credits for the person that did the editing on it, because that is it's a tough problem.
Yeah.
It's a real tough problem. And I would have paid a lot for an algorithm that would do that for me.
Yeah.
Well, to that end, have you sought out filmmakers? I mean, people who, that's what they do. They work in the world of cinema, narrative. They know how, a story works, beginning, middle, and end.
Right. Yeah, so in some senses, so I've been involved with some organization, for example, of workshops where we bring together, like we've had a couple workshops now on visual storytelling, which does try to bring together, computer vision side with the graphics side. There are even people within AI that their emphasis, independent of visual or not, is narrative intelligence and storytelling, right? And how you make computational models of that. So on the academic, joining forces side, we've been trying to get some of these groups talking together at such meetings. I think, these suggestions and thoughts about learning from how human editors do it is very intriguing. And there's just the biggest obstacle at first is availability of such data and willing, cooperating. These are the experts who do this would need to be interested. Right now, the editors that we have are in-house or crowdsourced kind of, novices, not the professionals.
I'm available.
Yes? Really? Okay, excellent.
Dr. Grauman, thank you so much. That was fascinating. Thank you.